Welcome to qnawire.
In this problem, we have a particle that is moving under a central force, and so the angular momentum per unit mass, h, is a constant. And if we use equation 12.27, we can see that h is also r squared theta dot. And since this is a constant, we can call it h naught. And h naught is defined by r naught v naught, the initial position times the initial velocity. So using that expression, we can find an expression for theta dot. So theta dot is simply r naught v naught over r squared. And so we can write this as r naught v naught, and we can write out r squared as r naught squared cos squared theta. And so one r naught cancels from the top and the bottom, so that becomes v naught over r naught cos squared of theta. So there we have an expression for theta dot, and we'll use this a bit later. So now we will calculate the radial component of the velocity. The radial component of velocity is Vr, and Vr is simply r dot. So r dot is the time derivative d dt of r, which is r naught cos theta. And from the chain rule, this is minus r naught sine theta theta dot. So that's the radial component of the velocity in terms of theta. Now, the transverse component of v which is v theta is equal to r theta dot. And using our expression for theta dot, or using our expression for r rather, we get this to be r naught cosine of theta simply times theta dot. So now we have both the radial and the transverse components of the velocity, and so we can find the speed of the particle v. So v, we know, is simply the square root of the squares, the sum of squares of the radial and transverse components. It's vr squared plus v theta squared. And this simplifies to r naught theta dot. And now we can open out theta dot, so this becomes r naught times v naught over r naught cos squared of theta. And now it becomes clear why we expanded theta dot. And so this is equal to, see the r naughts cancel, so this is v naught over cos squared theta. So we have an expression for the speed of the particle in terms of the angle theta. Now that we have v, we can actually calculate the tangential component of the acceleration. If we have the tangential component of the acceleration, we can use that to calculate the tangential component of the force. So the tangential component of the acceleration, at, we know is dv dt, the rate of change of velocity. And so this is v naught minus 2 minus sine theta theta dot. So we take our expression for v and we differentiate it with respect to time. So again, we'll have to use the chain rule. It's over cos squared theta. So this is equal to 2 v naught sine theta over cos squared theta multiplied by theta dot, which is v naught over r naught cos squared theta. So this simplifies to 2 v naught squared sine theta over r naught. Actually, this is above, this is cos cubed theta. So this becomes r naught times cos theta to the power 5. So now we have the tangential component of the acceleration. So since we have the tangential component of the acceleration, we can find the tangential component of the force. The tangential component of the force Ft is equal to m(at) by Newton's second law. And so that's the mass of the particle multiplied by the expression for the tangential force. So that's 2m v naught squared sine theta over r naught cosine of theta to the 5th power. So now we have an expression for the tangential force. So the tangential force we need to find in 2 scenarios. So in part A, theta is equal to 0. If we let theta equal to 0 into the expression above, we get that obviously sine theta is equal to 0, and so this tangential force Ft is equal to 0. For part B, if we let theta equal to 45 degrees and we substitute that into that expression, we get the tangential force Ft is 2m v naught into sine 45 over r naught into cos theta to the 5th power of, well, theta is 45 degrees, and we get that the tangential force simplifies to 8m v naught squared over r naught.